Think forward. Think Research Channel.
The opinions expressed in the following program are strictly those of the speaker. They do not necessarily reflect the views of the National Science Foundation.
From the National Science Foundation, where discoveries begin. This is Frontier, discussions of today's most exciting research subjects by distinguished scientists and engineers working at the frontiers of knowledge.
I'm Eric Sofji from Popular Mechanics, and here today we're talking about infrastructure. Specifically, how do we fix our dams, buildings, bridges, and roadways? Now, I'm joined today with an esteemed panel of experts. Here we have Linda Figg. She's President and CEO of the Figg Engineering Group. Also, we have Kim Rodis, who is chair of the Civil and Environmental Engineering Department at George Washington University. And live via satellite, we're joined by Matthew Rolfe, who's an associate professor at Georgia Tech School of Chemical and Biomolecular Engineering, and Yang Wang, who's an assistant professor at Georgia Tech School of Civil and Environmental Engineering. So just to explain how today's going to work, I'm going to ask a round of questions to our guests here, and then we're going to open up questions from the audience as well as callers and email. So to start things off, last August, a bridge collapsed in Minnesota. That sparked a national debate about infrastructure in the U.S., whether it's in crisis, whether it's crumbling. Our question here today is, how do we fix it, and what lessons can we learn from that, and what technology we can use to try to fix this system that seems to be in trouble, if not in crisis. So I'd like to start off with Linda. Your firm is actually working on the bridge that's replacing the I-35W Bridge. Can you tell us how the design of your new bridge might make it more stable?
Well, like you're talking about, this is a very important time in our history. And it's an opportunity for us to take advantage of the great technology that we have available in the marketplace to rebuild our infrastructure. And the I-35W, we hope, will be an example of that. It is a high-performance, high-strength concrete structure. And we're incorporating the latest technology that we have today, such as using sensors in the structure. It's smart bridge technology. There will be about 240 sensors throughout this bridge, basically 4 different types. Accelerometers that talk about the deflection of the bridge, and chloride penetration sensors that help us to evaluate the condition of the deck over the long term. Wire strain gauges that help us know about the stresses and temperature of the concrete. And, linear sensors that talk about the movement of expansion joints and bearings. And all of this is really creating a great database for the future. It gives us a wonderful resource of information that will help us become better designers for the long term.
Yang, you've also worked with monitoring systems in different structures. Can you tell us a little bit about your work and the results that you've seen?
Yes, Eric. Research focuses on developing wireless sensors for structural health monitoring. So now Linda just mentioned this monitoring system work in the instrument on the new I-35 bridge. There are also a lot of other bridges being monitored. I will give an example of a long cable-stayed bridge that's being constructed in Hong Kong. It's going to have 1,000 sensors on that bridge monitoring the bridge condition. Well, because it's a big bridge, it's very expensive to cable the whole bridge. So these sensors cost about $1,000 each. So the total cost of the whole system is about $1 million, this monitoring system. So we try to develop wireless sensors where you can get rid of all these cables. You can save your time for installing these cables, and you just plug those sensors on your structure, and they can measure the safety condition of the structure. They can do some simple analysis to the data and try to determine whether the structure is safe or not.
Matthew, if we are able to actually get the funding to build or reconstruct all these new structures that need to be fixed, Can you tell us about how we might be able to limit the environmental impact of all those new projects?
Well, I think the issue here is how to most effectively recycle the materials out of the existing structures. And so today we have developed very effective recovery systems for the metals and concrete and other such large mass components of many of the buildings and bridges. But there's also a lot of other things that are now inside of buildings, like ceiling tiles, carpets, molding around the sides of the buildings, and we need to be able to figure out how to recover those materials most effectively as well, so that we can avoid the material crisis that we seem to be facing with respect to the competition for things like cement and iron, ore, and steel that is being forced upon us by other countries needing to develop their own infrastructures at the same time as we're attempting to replace ours.
If we can increase the lifespan of these new structures going up, will that also, I guess, help when it comes to this issue of needing to recycle and the cost of that process?
Yes, I think that, again, if we're able to extend the life of these buildings and to replace the components as they fail, rather than attempting to replace the entire structure based on no real knowledge of exactly when it's going to end its life, that will help improve the material efficiency of our infrastructures, which overall do consume a significant fraction of the raw material and resources that are brought into the U.S. and mined out of the U.S. Infrastructures to be able to improve our overall efficiency as a society.
It seems pretty obvious what sort of benefits we'll have by sort of extending the lifespan of all these new structures or even ones that we're reconstructing. But I guess the question is how. Kim, can you address how we can actually do that in a sort of cost-effective way?
Well, I think that what it is if we think about when people are doing the design, whether you're doing the design initially for a new project or you're doing design for a renovation or replacement on a project, and you think about what information people have available to them to be able to do that design. And one of the things that we have for technology advancements that we are putting in place now, but that we need to continue to make better tools to be able to do this, is how do we get the right information to the right people at the right time. And this is an advanced computing problem. It's an information management problem. And so when we think about what we're doing with computational tools, how do we wind up using our advances in computing power to better model not only the structures that we're trying to build and maintain, but also the processes that we use to do that. So the kind of information, for example, about trying to design a bridge that would last longer that Linda was talking about, well, on shorter span bridges, often we can eliminate the joints in the bridges, and those are a part of the bridge that wear out very quickly. So when somebody is designing the bridge, they need that information about that's a critical thing for your design objective, is to have a jointless structure, and then how to get that executed. When we're trying to replace a bridge or a building, on the other hand, we'd want to have a model of that building. So what Matthew was talking about, he would know the person, he or she, the team of people that was trying to get this done, would know what kind of contaminants might be in there. What are the different products? How could they be recycled? So that idea about having building information models, which are really coming into their own right now, but we're just sort of starting on that. So in 2025, we're going to be designing our and maintaining our structures quite differently. And it's not just advances in the materials and the structural systems that we're working with, but also the information and the computational side of things. They tie together.
Well, Linda, you design bridges basically for a living.
Yes.
I think actually that's a good question. What do you think the bridge of 2028 will look like?
Well, it will be an extension of what is going on right now, but we will be looking at more improved materials. You know, we're being able to get better technology with materials, higher strength concretes, higher strength steels, fiber reinforced polymers. We'll be able to have more corrosion resistance in our materials, which is going to give us structures that will last much longer than they have in the past. I mean, we're looking at well beyond 150 years with the technology that's out there now. And this is great because the investment in our infrastructure is a high dollar item. And we need our infrastructure to last longer. And that's all good for sustainability and responsible construction. We need longer living structures.
Matthew, I guess we're also wondering what the sort of potential environmental impact is of these new materials that we're talking about, the sort of flexible concrete, self-healing concrete, all these sort of gee-whiz materials. Will those have a sort of serious environmental impact compared to what we've got right now?
Well, so the environmental impacts will be different, and I think that's the issue is that we have used a lot of the materials today, irons and steels and concretes for many years, and we have a reasonable understanding of what their impact is. But as we incorporate other materials such as nanofibers or nanotubes and other materials into those, we're going to experience a new set of environmental impacts. But again, that's not to say that that is necessarily good or necessarily bad. The issue is to be able to derive the information now to understand those impacts before we spread them widely throughout our society. So if we take the example of asbestos as a construction material, it was not very well understood when that material was used what its impacts might be longer term. But now that we've been through that experience, it's possible for us to do the testing necessary to make sure that these materials are safe before we deploy them in wide-scale use.
Yang, what role do you think sensors will or will not play in these new materials? Is it actually easier to install them, or is it going to make it more difficult?
I think those sensors will help you to use those materials more efficiently. The sensors will, like these wireless sensors, we hope that each single sensor, the price may be $5 to $10 in about 20 or 30 years. So this help us to have a very good feel about how the structure really acts in real life. We can have everyday constant monitoring. So with this accurate prediction to this structure behavior, we can have a more efficient usage of those new materials when we design a new structure. We can use them more efficiently.
I think, if I might leverage from that, another type of sensor that we can use is RFID, radio frequency identification tags. For example, those are very, very cheap sensors coming down now into the few cents range. It would be possible for us to actually place those sensors on individual structures and members within the structure, and then just go through the structure and actually inventory all the material that was actually in the structure with those type of sensors. So again, that gives us the opportunity to have a much better picture of what materials are there and how they have been used, and what exactly might be the way to recycle them in the future, to come back to a point that was made earlier. And it's this whole idea of substituting information for materials that is extremely important and can really lead to orders of magnitude improvements in the efficiency of our infrastructures as deployed today.
Kim, you've actually inspected bridges yourself.
Yes.
And I guess what I'm wondering is what impact you think these new sensors, or I guess any of the sort of technologies going on in terms of devices that can see into concrete to find cracks and devices like that, what sort of impact do you think that would have on inspections?
From my point of view, you have to remember that there's really very different kinds of classes in what makes up our infrastructure. And so when people think of bridges, they usually think of a major crossing, a signature span kind of bridge. And most of the infrastructure that we have is a lot more mundane. It's still very useful, and we go over them all the time. But most bridges that we cross are going to be 100 feet or less. So they're going to be more like a typical overpass that we go under all the time on a highway. And so for those, one of the things that I think is going to happen is that the kinds of sensors that have been mentioned, Linda in particular mentioned the chloride sensors. What are some of the things that really make those bridges fall apart right now? And one of the main problems that we have is the life of the deck. The life of the driving surface, which typically is going to be concrete with reinforced steel in it. The steel may be epoxy coated. But what we need to be doing is moving from those concrete decks that under heavy loading have lifespans of less than 20 years to something where we have a 40 or an 80-year bridge deck. And to do that, partly it's improving the materials and moving to things like composite bridge decks. and which many researchers are working on that would live longer. But it's also what Dr. Yang and what Linda has talked about here, about being able to know what's going on in the structure now, so that people that are planning how to maintain our roads can know. It's like going out and taking somebody's temperature to see, whether or not they're coming down with the flu. And they'd be able to do that for the decks on hundreds to thousands of bridges that were on their routes, so that they could do better planning.
Yeah, and with these bridge decks, I mean, traditionally it's been a reinforced concrete deck, and yet we have technology today where we can use transverse and longitudinal post tensioning to really gain extra strength in our concrete and compression, so that we can minimize that salt intrusion or the chlorides and give our decks a lot longer life.
I guess what I'm wondering is how long will it take to get them out of the lab, or what will it take to actually get these out of the lab and sort of into bridges, especially the rural bridges, the smaller bridges, that might not have as much traffic as maybe the I-35 West did.
Well, I think one way is to have these materials work in concert with other materials that we're very familiar with. I mean, one of the big components of bridges today is we must have redundancy. So having more redundancy by testing these new materials in with a system that's already designed to be self-sufficient with materials we know already helps us to be able to study those. For instance, there's a cable stay bridge in Maine where we put in the cables themselves have a few extra strands in the cables that we aren't really using for capacity. But instead of using steel, we've replaced those extra strands with fiber-reinforced polymer. So we have a real test case where we have this new material in operation in a bridge, where now we can look over the long term to see how this operates. And yet we're not really using it for strength, but we are using it to be able to see how this will work. So then maybe the next time we can use a little bit more of it. And this will help it get it into our marketplace much faster.
Hi, Jim Meggs from Popular Mechanics. That question about moving new technologies out of the lab or out of certain test applications that, as Eric says, we've written about many times over the years, and get them into common use requires that the customer for the infrastructure, typically the state or in some cases federal client, is interested in that kind of long-term thinking, in the value of a roadway deck that's going to last 40 or 50 years instead of 20 years. Are there enough incentives in the way that our infrastructure bureaucracy is set up to encourage that kind of long-term thinking?
One of the things that I'm involved in somewhat, but there's something that's called the Steel Bridge Collaboration, that is made up of the states and the fabricators for steel bridges. And so this is a case where the people that really care about having bridges work and really making the technology move into the marketplace are actually working together in a partnership, so that instead of having an adversarial relationship that you might expect between the owners and the suppliers or the people that are bidding on it, instead what they're trying to do is get together and say, how do we all make the specifications better? How do we all change the business model that we're doing on the bids so that we can bid to a computational model for the bridge instead of bidding to a paper set, which is just a very small subset of the information for the bridge. And so that's one answer, is that the system itself is quite interdependent and is very responsive. Now, unfortunately, this doesn't happen as much with buildings, because buildings have so many different owners. And so here you have something that's on the public side, and you might think that it's having less incentives because it's not as open to a pure free market, and the building side is. And it's actually been, when you look really in detail over the last 10 years about where the innovations are getting in, they're getting in more on the bridge side. And it's partly because you can have a modified free market, which is basically what we have for our public works system. So I think that that's a very interesting thing. And the other thing is that the Federal Highway Administration. So when we allocate the money through tax processes, the Federal Highway Administration does exactly what Linda's talking about specifically having technology transfer. The National Science Foundation does that. So the researchers that are involved in that, I believe Matthew and Yang both work with people that are really out in the field doing this. It's not like the academic researchers are divorced from the field. We go and work with these people. The other part, so that's the positive side. The negative side is that we as a culture are only investing about 2/3 as much in our infrastructure and have been since about 1980 as what we were doing before that. And I think that that is a decision that we have to make as a culture. So that's a different question.
Yang, we've actually talked about this in the past, how the U.S. sort of rates against China and other countries in terms of this sort of willingness to spend on infrastructure and on sort of things like sensors and other monitoring systems. How do you think we stack up right now?
I think, so from what I've seen so far, a lot of the recently most heavily instrumented structures, they are coming out in East Asia, not in the United States. I think one of the reasons maybe owners, the bridge owners or building owners in the United States, they are more cautious about their spending. They have to say, you know, this new technology, good, it looks good, but it costs money as well. How do I know that in the end, this this first cost of money can save money, can save me money in the end? Because, you know, we have to do a life cycle cost benefit analysis to the structure using either the new material or using a new monitoring system in order to ensure that the owner actually willing to pay this upfront.
I think the point there is that the information model that was brought up earlier is a very important factor in being able to demonstrate this life cycle cost. You don't actually have the bridge there for 30 years and then say, oh, and it cost X. You have to be able to predict the cost over the life cycle, which requires, that prediction requires that you have the computational model to be able to say, yes, if you make this investment, then this will be the saving that you will see 5, 10, 15, 20 years down the line. And again, in the public sphere where we do actually have the capability of looking out that length of time without necessarily responding to immediate shareholder value requirements, there is the hope that you could do that in those type of infrastructures.
We have a question from Isaac Cronin. He's from Berkeley, California. And Isaac is asking, what kinds of next generation materials are being developed to help bridges withstand impact from earthquakes to explosions?
Well, there's composite materials that are out now that are used to wrap concrete, which help give additional strength and also work within the issues of seismic and flexibility needs that are there. There is, all kinds of materials now that we have that give us greater strength in concrete, so that impact force, is actually can be something we can take within our design and even be streamlined in our design, not be as massive as what we might have seen in concrete elements in the past. And we have technologies in labs, such as in wind tunnels, where we can analyze the true characteristics of shapes and be real refined in the shaping of our structures so that they can withstand major hurricane events and still be serviceable afterwards. And so that is very helpful when we can look at that from a lab basis.
Okay.
One thing that we thought here was, again, thinking about materials is one way of going about making these structures stronger. Another one is the dynamic response, building that in. In other words, attempting to have the building itself be able to adjust as the shock hits it. That's another way of approaching this type of problem.
Yeah, this is a new technology called structural control technology. We put actuators in the structure, so when earthquakes or typhoon happens, those actuators can in real time generate forces to counterbalance the excitation. They try to reduce the structural vibration in real time. This actually helps to protect the structure.
One thing that I'd like to address, it's kind of the elephant in the room, is the issue of money and how we're going to pay for everything we're talking about, from bridges to dams to levees and especially all this physical infrastructure that's not managed necessarily by private companies. And I guess I'm just wondering how you think we can get the public interested enough, or politicians, anyone interested enough, to actually pay the money we think we need. And so I guess I'm actually interested, Matthew, in, because I feel like a lot of your work involves sort of cost cutting and such, especially with recycling.
So I think that the answer is that it's been demonstrated time and again that the public responds when some catastrophic event happens. They see the impact of having a bridge fail, and that these are the opportunities then for politicians to use that public goodwill to move us forward in terms of making these investments. I think the other thing is that, again, using models to demonstrate to all stakeholders, whether it be politicians, whether it be the general public, that building a smarter structure or building a stronger structure can, over the long term, save the public money is a way to go about this. I think it's a failure sometimes of communication rather than anything else, that we haven't communicated the case for these kinds of investments well enough, rather than it being that people aren't willing to make the investment once they see that there is indeed a return on it.
The need is overwhelming. I mean, there is, when you look at bridges, you have both the functionally obsolete, which means they aren't wide enough, they don't have proper shoulders, they can't carry the amount of traffic that's really needed to push through that corridor. And then you have the functionally, the deficient structures, which are, just the wear and tear of the bridge needs to be replaced because the materials are failing. And when you combine those two, it's an overwhelming amount of money that's needed to repair and replace our infrastructure. So it's not going to be one source that's going to be the ticket for one size fits all. It's going to be multiple sources. I mean, we're going to need state and federal money. We're going to need to look at tolls. We've got to look at how can our local resources or even developers help with some of this. It's really multiple scenarios. And for instance, one example would be how we take a corridor that is just packed with traffic and try to expand it within the right-of-way and maintain environmental sensitivity. Perhaps there's a way, like where we can build up through using the median to build a structure. We did this down in Tampa, where we have a 6-foot wide pier, but on top of it is a 3-lane structure that is reversible. So in the morning, if you live out in the suburbs, you take in 10 minutes, you get down to the city in these 3 lanes going in town. In the afternoon, it reverses, and you go 3 lanes back out, and you pay a toll for that opportunity, $1.50. But you're out of the traffic, you're nonstop, and it doubles the capacity in the existing right-of-way in only 6 feet of space. So there are ways in which we can really manage our traffic and offer free and tolls and get the job done in kind of a multifaceted approach. And
public transportation is also sort of incorporated into that project.
It is. I mean, it doubled the bus system, which wasn't, it was only functioning slightly. But now what happens is people park at an outside mall, get on the bus, and it doubled the buses going back and forth because it was reliable. Now you have guaranteed delivery at a particular time.
We have an email question that is addressing, well, this issue indirectly of congestion. Stephen Wonker, who's from here in Arlington, is asking, are there new technologies that will replace or improve E-ZPass and make it available to more people, which would in turn contribute to the elimination of traffic bottlenecks?
One of my colleagues at George Washington, Azim Eskandarian, does quite a bit of work in intelligent transportation systems. And so that's one of our main labs in our department. And yes, there are indeed technologies that would do that. And not only would they, again, it's an issue about what transportation services do we want to be delivering. Because one of the things that they are doing is not only looking at the thing about making the E-ZPass more available to other people to reduce the congestion as you're going through the particular tolls, but looking at applying what London has done, which is applying pricing so that you have tolls that are based on the congestion. And so what happens is you pay a toll for riding on the normal surface roads, not the toll roads. And that is priced according to the time that you're driving around London. And that has been very effective at reducing congestion. And so that is something that is specifically discussed in Arlington in the Northern Virginia area, which is one of the 10 most congested areas in the country. Since I have the floor for a minute, Eric had asked the earlier question and Linda had talked about structurally deficient versus functionally obsolete bridges. And remember that we do have a huge amount of our country that is semi-rural and rural. And so one of the things that I was able to do for research, which was enormously satisfying, is the Department of Transportation in Kansas funded me with 2 different doctoral students to work on how do you take bridges that are on rural routes. So they don't carry very many trucks per day. But they're very important because if you take one of those bridges out, they can easily add 50 miles for what you have to do for the detour. So they're very costly from a market, delivery to market point of view. So what we can do is when that bridge needs to be redecked, which is usually the first thing that happens, if the problem with it is out-of-plane distortion cracking on the girders, which is 80% of all of the cracking problems in the United States on our highway bridges are due to that one cause. And if that's the cause, and it's not functionally obsolete, we can go in and we can redeck it, and we can fix those girders when they're doing the redecking for 3 to a maximum of 10% of what it would cost to put in a new bridge. And so instead of, that would mean that you could put in 33 of these fixes instead of putting in one new bridge. So that's part of the thing about trying to have our system providing the traffic services, very much what Matthew was getting to, about you don't have a one-size-fits-all solution.
Matthew, you mentioned that the impact that a sort of bridge collapse can have on people's awareness of infrastructure. When it comes to buildings, for example, or just anything that isn't a bridge that doesn't collapse in that dramatic of a fashion, what do you think can be done to sort of raise public awareness?
Well, I think you've seen a tremendous growth, for example, in certification of buildings from an environmental performance perspective. So there is this green building certification system called LEED, which has been adopted quite widely throughout the U.S. A number of state and federal agencies require their buildings to be certified in this way. And so that has created an incentive now, and they've demonstrated that these buildings can actually be cost effective. So they've tied environmental performance and a simple grading system of bronze, silver, gold, and platinum levels to the overall performance of the building. And so I think we're seeing a spread of these kinds of green standards to other products. For example, I have recently been involved in the development of a similar standard for carpeting. So there is in fact now a standard available for carpet so that you can get silver, gold, or platinum certified carpet that has, again, an overall environmental profile that is lower than other types of carpeting for commercial buildings. And you can help, that product can actually be used in buildings to gain you points towards the LEED system so that you can actually have the LEED certification more effective. So as we start to develop these standards, so we can actually see an increase in the use of sustainable products and sustainable standards to help improve the overall efficiency, both in terms of material and energy in these environments. And I think there is now much more awareness in the public sphere of these kinds of standards.
And Yang, do you think that there's a way to sort of leverage what happened in Minneapolis to sort of help people understand the impact or the sort of benefit of monitoring systems, particularly in bridges, but I guess in any structure that could conceivably collapse?
Yeah, certainly. I think a lot of departments of transportation are now paying a lot of attention to their bridges. And for the buildings, particularly those buildings either in earthquake zones or in typhoon zones, these high-rise buildings, a lot of them are actually being instrumented with sensing systems for monitoring their behavior. Like the 1989 Loma Prieta earthquake in the Bay Area, there were actually buildings in San Francisco that were instrumented with sensors. But nowadays, with those sensors, the price of those sensors getting lower and lower, we are expecting to be able to instrument more building structures in the future.
We actually have another question that's emailed into us. It's from Jimmy Camp. He's from New Mexico. And his question is, the budgets for bridges have been relatively flat in the U.S. for several years. However, costs have been rising fairly rapidly. Are there any low-cost initial solutions on the horizon?
You know, I think that where we can gain our greatest economy in bridges is in these new materials and in the strength that we can gain from them. So, you know, for the high-strength concretes and high-performance materials, it helps to drive a lower cost. For instance, there is a concrete called self-consolidating concrete. And basically what you do is it pours like a liquid. And this reduces the amount of labor that it takes to actually pour and put the concrete in place. And labor is really one of the biggest cost factors in the development of a new bridge. So when you can help streamline the efficiency of construction, that's really where we can do the most in terms of benefit of the cost of our structures. And plus, we are going to be faced with a labor shortage in construction as we move forward in this country. And so we need to look for more efficient ways to be able to construct.
Well, actually, can you talk more about that issue? Because I wasn't aware of that problem, that we are going to face a shortage of labor.
Well, there aren't as many people going into the construction arena. And so in the future, we really have to do more to recruit, both in engineering and in construction. There are predicted pretty major shortages coming up in the future. And so, you know, anything we can do to inspire our young people to go into these professions would be, you know, outstanding.
Well, yeah, actually recently I was at MIT looking at a proposal for a sort of automated system that would essentially weave a structure out of composite materials, almost like using yarn to basically create sort of a tube. And I guess I'm just wondering what the sort of impact you think automated sort of construction could have on this industry. I mean, obviously, I thought that there'd be an issue of maybe sort of stealing jobs from humans, you know. But I guess if that's not an issue, it sounds like that could have some real benefits.
Well, and whenever you can prefabricate elements in a controlled environment, not only do you get speed, but you get economy because there's a repetition of the development of those elements. It's similar to the process that we're using on the I-35W Bridge because the main span is made out of precast box girder segments that are actually prefabricated on the roadway on the south side of I-35W roadway. We're prefabricating them in these shed areas. And then these segments will be trucked down, and then it'll be like big Legos being put into place. And then you gradually add these next to each other until they meet in the center of the 504-foot main span. And this can then be done in terms of assembling these segments in, about 8 weeks or something like that. You all of a sudden have a 504-foot main span. But it's in a controlled environment, so you really have a lot of great quality control. It's ease of fabrication. It's easier to do that over land than it is over water. So, so you really streamline the process that way.
Okay.
Thank you. Hi, my name is Richard Spivak. I'm with the National Institute of Standards and Technology. And my question is, public infrastructure, by definition, is public. Do you see now or in the last several years a commitment by the Fed or the state locals to spend the money necessary? And if you do, where's it coming from? Is it Fed-driven, state-driven, local-driven?
Well, I don't think that infrastructure, the way that we deal with infrastructure in the United States, that it's inherently public. There are things that I think that, for example, the medical infrastructure depends on hospitals, and a lot of hospitals are private, not public. So I think that we have a much richer economic model and a lot more options than that. But we do have a real problem, and I think people keep referring to that it's very clear in the last 30 years that we have not, as a society, been putting the money into the public part of our infrastructure that is necessary to maintain and extend that infrastructure. And the American Society of Civil Engineers, again, we get back to communication issues. And Matthew talked about the LEED system. Well, the American Society of Civil Engineers has the report cards on the infrastructure for the United States. And it goes through and it looks at 18 different categories, I believe. And it looks at bridges and airports, which we haven't been talking about, but are another thing, schools. And it's pretty clear. And it's pretty clear that people agree on kind of a ballpark that we're spending about 2/3 of what we need to be spending on that. I mean, some people may say a quarter. Some people may say that we're spending half for the variation.
Well, it's really a combination. I mean, there is some, our U.S. highway system predominantly gets funded through federal funds. But there's usually a match with the state. And then we also have some state, and then, of course, local is always an interesting dilemma because, you know, our funding is stretched so thin amongst so many needs that are out there. But it's a very important question for today. It's one that has to be answered because from the year 2003 to 2006, our cost for infrastructure grew by more than 40%. And so that is, you know, just in basically the bridge that you went out to build in 2000 now costs 40% more than it did then. So now, not only are the needs still great, but you don't have, your money doesn't go as far as it used to. And so we have to find now a way to use that money more wisely so that we can have a longer living infrastructure and not have to be replacing as often.
This is Ken Chong from the National Science Foundation. I think one of the main reasons for the damages in any earthquake is because of the mass or the weight of the bridges. So the lighter you make the bridge, the easier it is to withstand the earthquake. So about 10 years ago, I proposed some kind of intelligent bridge. So some of the features I'd like to mention to you, and I'd like to check with Yan and others to find out what is the state of the art of that. This futuristic bridge is consisting of very advanced composite materials. It could be nanocomposites. It may be 10 times lighter than the conventional bridge. So the moment of inertia is much lighter. So in an earthquake type of situation, you wouldn't have that kind of damage. But in a wind situation, your car would be galloping, okay? So you need a lot of sensors, you need a lot of feedback control and actuating and a closed-loop system for this active or passive control, as Yan has mentioned. So this is one of the features that I proposed. Another feature was some of the optical fibers could be used as sensors, which could also be part of the structure itself. So it's a continuous sensor. It also have self-healing type of materials. It has smart paint. It has geothermal energy that you can pipe from the riverbed to de-ice the deck. Mm-hmm. So those bridges in the northern hemisphere or colder temperatures is a very green technology. So those are some of the features that I propose.
Well, Yang, I think he was wondering particularly what you think about that proposal.
Yeah, hello, Dr. Chong. There has been a lot of research going on in nanotechnologies. I think Dr. Chong is one of the experts in this area. I have not done work in that area, but I think there may still need a little bit more time for the researchers to be able to bring those technologies into practice, like this smart paint that Dr. Chong just mentioned. So when we talk about sensing, before we are using sensors, these are discrete sensors. You can only put them on individual points on the structure. But in the future, if we have these smart paint sensors, I know there are researchers in the University of Michigan and also in the University of Maryland working in this area. So you can paint those all over your structure, and this paint is acting like a sensor. If there is crack happening on your structure surface, it can actually capture it right on. So you don't need to worry about, this sensor, I put it here, it may be missing a crack position. So I think there are a lot of opportunities. It's a lot of work being done in those areas, but we are hoping to see to to see them being applied in realistic structures in the future.
So I've got a question from Kate Schweitzer from New York. She says, what are the difficulties in managing infrastructure when it's under the jurisdiction of more than one entity, or in some cases owned by private citizens?
This gets back to the question that was asked earlier, and I think that on our roadway system, if we just restrict it to that, to the national highway system, I think that the leadership on that normally comes from the federal level, because that's where the gasoline tax is set. And one of the problems that we have is that the gasoline tax has been at the same level since 1993. And it's a level on cents per gallon. And so it's not a percentage level. So as the cost of gas rises, it's still the same number of cents that comes out of every gallon. And so I think that there's been a real failure at that level, that the system's not working. Because, so I think that's where it goes. So then you get to this question about, well, how do people wind up working together with it? And I think that gets back to a systems approach. That what you need to do is you need to have the different stakeholders in that situation make explicit what it is that they're trying to accomplish. So for example, one of the earlier ones, is there any technology out there that would be a quick, inexpensive fix for our highways? Well, yeah, get the trucks off them. Because, right, I mean, the bridges can carry, most of the bridges that we have on the interstate system and the national highway system right now could have well over 100-year lives, several hundred-year lives, if it was just passenger vehicles that were on them and not trucks. So that's exactly the kind of system question that Matthew was talking about really what are we trying to get? Are we trying to get goods to market? In which case, why aren't we using more barge traffic and more rail traffic instead of using truck traffic? So the thing is that you have to get the stakeholders together and make a decision. And it's much easier when you have a physical piece of infrastructure. For example, the new bridge across the Potomac here, which is partly in Virginia, partly in the District of Columbia, and partly in Maryland. And so when there's an accident on the new Wilson Bridge, they have to be sure who they call and how they coordinate it, because you may need Washington, D.C. people in the middle of it, because they own the middle of the bridge for the emergency services. So I think that is an example where the Federal Highway Administration was able to pull together and do a very good signature process project that went across multiple areas. But we have this big problem, you know. From the technology side, we can try and solve the problem right. But you have to look at engineering in a broader societal context if you want to say, are we solving the right problem?
Well, and if we look 50 years ago at our design codes, we had a particular code we were designing to. Now we look 50 years out, and during that time, we really expected our structures to last about 50 years, and we were going to be replacing them at that time. Well, also, our truckloads have gone up by like 25%. So maybe forward thinking, we look at how can we design facilities that allow us to add additional strength and capacity in the future without having to completely replace them. And also consider how can we go ahead and design now for mass transit or light rail or you know, other types of trains on the structure, so that 100 years from now, we can handle those loads. We can go ahead and accommodate that on our existing infrastructure. And so those are the kinds of thought processes that we see going on in infrastructure design, so that we can look more broadly at the future.
We actually have an email from Jay Bussell, I think, and his question is, do you see composites becoming more mainstream in bridge construction, whether they're all composite decks or rebar used in concrete decks?
We certainly need more information today. There are all different kinds of composites out there, and there's a lot of research that's being done both by the Federal Highway Administration and other technologies. So it is something I think that we have to look at. We have to look at our new materials, especially when we're looking for things that can be corrosion resistant and that can give us a longer life. These new materials have different properties, and so we have to be able to address those, whether it's you know, fire resistance or you know, their ductility or how they handle UV light, and all of these things can be addressed. We just have to make sure that we've studied them properly and we put them in the right application.
And how much of an impact do you think you can have on the entire industry? It seemed to us, when we visited the site there especially, that the pace of construction and the sort of the attention that it was getting from tourists, every weekend there was at least, I think, 100 people, we were told, were stopping by. What sort of impact do you think you can have on this entire sort of movement of sort of fixing our stuff better, faster, maybe even cheaper in some cases?
Well, one thing that came to light with this bridge being out of service was how important bridges are to our local economy and our quality of life. I mean, it represents anywhere from $400,000 to $1 million a day in lost economy because that link is out. It's a major interstate corridor. So, this is so vital that it be done very quickly. By being able to combine design and construction, in the same interface team, and to be able to construct multiple components of the project at the same time, we're able to fast track this. So in the first 6 months, the design was complete and 50% of all the concrete's been poured. We do have a balcony view of the project because it's right next to and parallel to the 10th Avenue Bridge, which has a sidewalk. And every Saturday, there is a sidewalk tour. And like on this past Saturday, there were 200 people from the community that came out and met with the project manager for Flatiron Manson, the contractor who's accomplishing this work. And he gave them a tour of the project from that balcony view. Certainly through our webcam that's 24/7, and there's 2 webcams, and you can kind of zoom in on the construction, and with one of them, all eyes are on us. And so everything that we do is to look at how we can do it better and how we can improve what we're doing. And so, that we hope that this will be something very positive for America as we look for our, improving our infrastructure in the future.
Okay, well, Matthew, is there anything else that you think you'd like to address before we close this thing up?
Well, I actually wanted to return to a point that was made earlier by Linda, which was this whole question of thinking of construction more as manufacturing and less as a one-off kind of project. I think that that's a very important point as we move forward, both in terms of speeding up the construction and also being able to make many of these structures. As was pointed out, there are hundreds of bridges, but we always tend to think of the signature projects that are done. We need to think of this as we have hundreds of bridges of very similar type, and if we could develop manufacturing processes around those bridges that would standardize and modularize those, we could very much improve the effectiveness of our construction and reduce the cost, both through the application of advanced materials, but also, again, through the application of advanced manufacturing techniques. I think it's very important that we bring those two things together and think about how we can design those together as a system. The other point I wanted to make is we've talked a lot about this issue of services. And I think, again, we have to start to move away from thinking about constructing specific bridges and specific roadways and think about how we're providing services and how we create the right incentives for the different stakeholders to come together in a positive, non-antagonistic way to deliver services to the public, and the public provide the funding for those services rather than providing the funding for specific roads, bridges, and other such pieces of infrastructure.
Yang, any closing comments?
Yeah, I would like to take this chance to ask for more support from the society in our research. We have seen a lot of instrumentation in bridges, but we have not seen that many being published in buildings. One of the reasons is that for building owners, if you would like to instrument their building, they worry that their rent may go down. Because when people see this building being instrumented, people may wonder, is there something wrong with this building? So this sort of non-technical barriers actually exist for us to put out those technologies to make them more useful for the public.
Kim?
Well, I want to reinforce what Matthew said about we're doing this paradigm shift and that we need to be looking at civil and construction, the big difference between construction and manufacturing. And instead of looking at construction, which inherently is a one-off, that we look at it more as a manufacturing process. And the building information models and getting back to looking at the overall system that you're designing. And I just wanted to put an example in here on buildings. There was a new automobile manufacturing plant that was built in the Midwest a few years ago. It's about 3 years ago that this was done, and it used building information models. And the old adage is when you want something for an engineering project, you can either have it inexpensive, so the cheap, you can have it so you can have it be on or under budget, which is the cheap one. You can have it be on or under schedule, which is the fast one, or you can have it be quality, right? So that you can have it be high quality. And the joke is, which two of the three do you want? Okay? Because you can only get 2 out of 3. Now, what this really proved is that not only if you move to a smarter way of working instead of just working harder, that we really need to be working smarter with what we're doing, is that they said not only can you get something that it came in under budget, ahead of schedule, it was very high quality, and the site was safer. Because what it did was it cut down on waste materials. And specifically, just having the building information model cut 3 dumpsters that they had to have on site that were emptied daily. 3 dumpsters were eliminated because they eliminated that much scrap metal in one day. And so the thing is that we have an enormous can-do ability to do good engineering. And I think that as a society, we all want to work together and be well-informed. I think better decision support, more research, getting it into delivery. So this is a whole approach, and I think that NSF is really championing that. Popular Mechanics is really addressing an informed part of the public about how to make this happen for the future.
Well, it's outstanding that we have an opportunity to have this open discussion and talk about technology, and I think all of us here feel thankful to Popular Mechanics and the National Science Foundation for opening this dialogue. And it is through this awareness of technology that we're able to further implement it into our projects and make it progressive and give us an opportunity to really advance American infrastructure. And so, I want to thank you all for giving us that opportunity to have this discussion.
Well, I guess I'll thank you right back. I actually want to thank the whole panel. And for more information, you can also just head to nsf.gov/bridges or to popularmechanics.com. Thanks a lot.